LeetCode 994, Rotting Oranges. Given an M by N grid, each cell can have one of three values. 0, empty. 1, fresh orange. 2, rotten orange. Every minute, or every step, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Return the minimum number of minutes, steps, that must elapse until no cell has a fresh orange in it. If this is impossible, return -1. So given our picture, diagram here that they gave us with these oranges in here, we would go from minute 0, we would find the adjacent oranges to minute 1. We got 1 per step, 1 orange per step. So for each rotten orange, we can go 1 step. So for this rotten orange, we can go left 1 step, right 1 step. There's nothing above it and nothing to the left, but we can go right and down. Now we have 2 new rotten oranges. And we're done with this one. We've already eliminated that, so we remove that one. And now we can go for these 2 here. So we go to this one, we go to the right, and to the one above it, we go to the right. And that gives us minute 2. And then for minute 3, we can only go down for this one. And for minute 4, we can only go across for this one. This diagram isn't 100% representative of what goes on in the code. What actually happens is when we start, we take one off of the queue and we rot the adjacent oranges. And then we add those to our rotten oranges queue. And then we do the same thing for the next one. Now, but what happens if we have an orange that is sort of orphaned in the bottom here? Well, not orphaned, but we have 2 rotten oranges. That's what I meant to say. 2 rotten oranges. For minute 1, if this were our example in minute 0 here, if this were our actual example, minute 1 would look like this, because we would start from 2 directions. And then we would eliminate these 2 from our queue. We would go to minute 2, we would go here, and then we would eliminate those from our queue. And then we would be done in minute 2. Now we have to think about another case. Think about this case where we have a rotten orange in the upper left and we have a fresh orange in the lower right that is kind of orphaned. In that case, we won't ever be able to reach that one with a rotten orange. And we can see that in the beginning, and there might be a way to efficiently detect that. And if we were getting a lot of data like this, it would be worthwhile to do so. But to walk through the algorithm, we can rot the adjacent oranges. Okay. Minute 1. Rot the adjacent oranges. Minute 2. We got 2 new adjacent oranges. We still have a fresh orange. In minute 3, we try to rot adjacent oranges, and we have the same number of fresh oranges. We have no new rotten oranges. So we know that we can't rot any more oranges, but we can't reach them all. And in that case, we can't give the number of time until each cell has no fresh orange, because it's impossible. So in that case, we would return -1. And the way I've implemented this is with a breadth first search, but it's more complicated than a flood problem where we just have one node to start with and we branch outwards. We have multiple nodes. So we have orange in the upper left, rotten orange in the lower right, and we have to branch outwards from those simultaneously. So it's harder than a flood problem. So the way to do that is to keep a queue of the rotten oranges, and that's actually done with an array, and shift one off the front, and then rot all the oranges. So we get new rots from each one that we shifted off the front, and we put those in the back. So how do we determine what a minute is? Each minute occurs when we can push new rotten oranges onto there. So while we shift off of the rotten oranges, while we have fresh oranges, Then we try to shift one off of the rotten oranges, and then we push all the new rotten oranges onto there. And if we didn't get any new rotten oranges, then we return -1 because we still have fresh oranges. But if we did get rotten oranges, then we push all of those new rotten oranges on to the end of our queue, rotten oranges queue. And so that would be 1 minute. So when we visit a rotten orange, we get all the neighbors of that orange. The neighbors are, in a graph, would be the previous row, the next row, the previous cell, and the next cell. Those can be undefined. When you think about when you're in the upper left corner, the previous column and the previous row are undefined. And when you're in the upper right corner, the previous row and the next column are undefined. And so that puts a lot of conditional stuff in the code, and we have to consider about what the value of the j minus 1 is. Okay, that's going to be previous column. I minus 1 would be previous row. I minus 1 square bracket j minus 1 would be previous row, previous call. It just becomes a little less clear. And so what I did is I implemented it with an ECMAScript class to have T, R, B, and L properties on an orange object. That makes it a little clearer. So what I do is I loop through the values of the orange. The values of the orange are, you can see R, L, B, and T. But the way this is initiated in the constructor here is a little bit creative. So what it results in is a tiled matrix where each tile has a pointer to its adjacent tile. So this orange, which could actually just be called a cell, has a pointer to whatever's above it. So in this case, if there's something next in the grid, for example, if the grid is this grid right here, if we have a next cell in the grid, we've got a cell index and a row index. We start at 0, 0, and if we have 0, 1, then we're going to add an R property to that orange object. And then to that R property, we're going to add an L property, and that's going to be pointing back to this. So we say, here's the next orange, and the next orange is R property, our orange. Here's the R property of us, it's the one in the next cell, and then the L property of that next cell's orange instance points back to us. So we create a back reference to it. So we do create circular references. So R points to L. All right, this R points to the next orange, and the R.L points to this, and R.L.R points to that, R.L.R. You keep going back and forth. So we create a pointer, a dual pointer, so it points to the next one and points to the previous one. And we get the same thing from the ones above and below it. So when we check through the next row, when we want to see what's below that upper left orange, we can see if we have one. And if we do, then we assign a B property to it. And then to that B property, we assign a T property, T for top. So B would be the one below it, and T would be the one above it. That gives us the ability to have each orange have a B, R, T, L, or T, R, B, L properties, top, right, bottom, left. But you'll notice actually that not all of them have these properties. And that's fine, it doesn't matter. If it doesn't have the property, we just treat it as if it's not there. It's the same thing as not having it. So we loop through these by getting all the properties off of these rotten oranges, the values of them, the T, R, B, L. And the values are going to be 0, 1, and 2. That's represented in the val property up here. This is a private property, as you can see with the octothorpe. Before a val, it makes it private. And then we have getters and setters here to get that property. These getters and setters do not show up in for in or for of enumeration. They don't show up in enumeration loops. So we won't get val exposed down here. We'll only get the TRBL properties exposed in this. Now I know you're probably thinking, well, why couldn't you just create a neighbors property? I could have. We could have orange.neighbors.trb and L. Could have. But I just made it that way because it's kind of for the brevity of being in LeetCode and not quite being into an object-oriented solution, but being good enough for LeetCode, but a little more object-oriented than necessary to make it maybe a little more readable or realistic. Something that I would prefer to see in actual implementation code, where we would have a class and we would have properties. And it wouldn't even necessarily have to be a class. This could be implemented as a function. Could be even just a plain old JavaScript object with TR, B, and L properties. The TR, B, and L properties make it a little easier to deal with. So now we only have to deal with neighbors, and we have to deal with the neighbor's value. We don't have to go through all the I minus 1, J minus 1, I plus 1. If it's undefined, there's none of that conditional logic in a loop. So let's go one more free focus on this algorithm here. Count the minutes. First thing we do, this algorithm counts the minutes, counts minutes, calls init oranges. Init oranges, all it does is create a new orange at 0, 0. The new orange being created at 0, 0, then initiates the orange grid. So now we have a grid of interconnected tiles. It's like a linked grid. There's probably a name for this data structure, but that's what it is. We have T, R, B, and L properties on each orange, and it recursively creates itself. We see orange.getOrange. Now this is also necessary to have this getOrange method, because if we were to just say new orange, we would end up with way too many oranges. It would be infinite. So we would get the T property, and that would be the top. That would be undefined. But what if we were in the middle cell? We got the T property. That would be the top one. We got a new orange for it, but we already created an orange for that one, right? So then we would be creating a new orange to get the bottom property of that one, and it would be infinite. So rather than just getting a pointer to that orange instance, we would be getting a new one. So in order to avoid the infinite orange creation, we have a getOrange method, and the key for that is they're stored in a map. The key for that is the row index plus the cell index. So we get that based on the key. So if it's row 0, column 0, the key would be 00. If it's row 0, column 1, it would be 01. If it's row 1, column 0, it would be 10, and so on. So that's how we've gotten that. Now, I know that this could probably fail if we were to have like hundreds of columns. We would have maybe some ambiguity between 10, 100, or 1010, right? That could be an ambiguous problem. But given the data constraints, we don't have that here. So they don't even say what the less than 10, right? So we don't have that problem down here. So we could put a comma in there if we wanted to make the key to separate from the row index from the cell index, but I just put it as a plus because the constraints are small enough. And then we get the key, and then we get our orange, we get our adjacent orange. Back to this algorithm again. We shift one off of while we have fresh oranges, we increment the minutes, we get a new rots array, and then we loop through the rotten oranges, shift one off of it, and then push those onto there. And so we shift all the rotten oranges off of there, right? And then we get new rots. And then if we don't have any new rots, but we still have fresh oranges, then we return -1. Otherwise, we push all the new rots back onto our rotten oranges array, so that thereby repopulating our rotten oranges array. And then we continue this process. Well, we still have fresh oranges. We continue this process. We take all the rotten oranges off. We rot all the adjacent oranges next to them. If we didn't get anything new, we return -1. But if we did get something new, then we rot those oranges, take those oranges out of the fresh oranges, and add those to the rotten oranges. And the way we take them out of the fresh oranges is done in the visit method, and it's using a set. So we just call freshoranges.delete, and we delete that from the neighbor. And delete is a keyword in JavaScript, but it's also the method on set. So set.prototype has a delete method. And so that's how that works. We delete those from the set of our fresh oranges. So yeah, it's there's a few ways to do this. As you can see, I've got a bunch of commented out code down below. The commented out code was actually cleaner, but it was super inefficient. It was like way down in the bottom of efficiency levels. And this one is, I'm not going to lie, it's not, you can see that I did a bunch of them. it's not very efficient. It's not super efficient. It's down on the bottom for memory. Now, one that I did a couple of years ago for this is, let's see, here we go, was much more efficient. And it used a different approach. Rather than creating an orange tile grid, I basically assigned each orange instance as a property to replace the cell value for the grid. And you can see that in here, where we have cell equals cells I equals new orange. And the cells are actually the rows for this grid. The cells, it's actually the same thing in this grid. So our init orange is grid, and this rows is actually the grid. And then for each row, we get the cell, and then for the cell, what we do is we modify cells J, and we create a new orange instance. That was actually way more efficient, as you can see. Now, a couple of things have changed. Number one, obviously the code is different. Number two, LeetCode has changed their implementation, so they have different JavaScript implementation now. So we're not getting the same performance on this due to different code, and I think this code is actually better because, number one, it doesn't modify the original grid. And in JavaScript, it's always a good idea to not modify objects that you don't own. So if we're passed in a grid and we have a side effect of modifying that grid, that two-dimensional array, that side effect could be externally observed. Right? There might be other code that's relying on that grid, and they just passed us that. And that would be a problem, because then we could be affecting other code, and we wouldn't even be clear of where that effect was happening or what was causing it. The other way to mitigate the problem of don't modify objects you don't own is to always return a safe copy. So if I'm creating an array and I'm using that array internally within my own class or algorithm or data structure, and I return that, I expose that array to somebody else, to some other API, and that other API then modifies that array, that can cause a problem for mine. So in that case, to be defensive, return a safe copy. So copy the array and then return a copy of it so that they can modify that copy however they like. It's not going to change anything to anything inside of this array. That can be a little difficult when we have multi-dimensional arrays, but it's generally a good practice. It's safer to, when returning arrays that you might want to rely upon, to return a safe copy. And that's all I have to say on the matter. These are some design considerations that you just normally won't get in LeetCode problems because of the competitive algorithmic nature of LeetCode, where they want you to get the best memory and the best performance, time performance. And what is the big O notation for both of those? And we don't have any bragging rights here, right? The only thing we can say is, well, it's a little easier to read in this visit method and in the count minutes method, because now we only have to deal with a small amount of code. We don't have to traverse through the graph. That's not something that can be metrically measured. That's just a human factor of reading the code and, oh, okay, that's a little easier to read. Now, the harder part to read is the complexity of the code, where we've added that complexity into the orange instance and our getOrange method. And so we've encapsulated some of that complexity into an object, into a class, but then kept the algorithm a little more straightforward. Taking this one step further, it's hard to imagine implementation code where we would have this sort of thing, but it's possible where we could have such algorithm where we would step through and rot oranges one by one, or have some other sort of multi-point flood algorithm. Right? We had maybe a missile lands on one part and a missile lands on another part in a game, and it has to disperse and destroy the cities that are nearby. Something like that. If we were going to have something like that, we could make this even a little more sophisticated, because there might be even more logic that has to do with that game and the missile disbursement and the cities that are adjacent. And that instead of an orange object, we would have a grid object, and that grid could be a city, it could be forest, it could be lake, it could be any number of things that might exist in that terrain. And in that case, we could have a grid object, and that grid object could then delegate to more other things. And that's where we start getting into the design aspect. We have object-oriented stuff. As far as the algorithm goes, well, graph problems do tend to be algorithmically messy. And the way that I prefer to handle them is by encapsulating some of that messiness of previous row, next call, previous call, into an object that has a T, R, B, and L property, respectively. A lot of considerations and thought. Thanks for sticking through to the end of this video, and I hope I hope it was worthwhile. If you have any suggestions for improving the performance of ECMAScript 6 classes from the lackluster performance I'm getting here, hey, I'd love to hear that. And in some of these others, they're actually quite a bit worse, as you can see. And there are other solutions that I've come up with in here. I've worked on this problem for quite a bit. So it's not as if I just came up with it. I thought it was worthwhile to share, even though it's a little bit strange. So I think it could be even better. And I think there's probably a way to improve the performance and improve the readability. And that's a constant goal. Try to lose fat and gain muscle, always.